Thanks for coming. I know it's a difficult time after a wonderful keynote by Venkat, and I know it blew our mind, at least it certainly did. I love seeing his live demos. Today we're going to talk a little bit about resiliency and availability, and in particular about failure. I'm kind of passionate about failure and chaos in general. I'm working currently with Amazon Web Service. I'm a technical evangelist with the company. And for the last 3.5 years, I've been working with a bunch of customers, trying to help them scale and build resilient architectures. Prior to that, I've been working in several startups and companies for the last, let's say, almost 12 years. I was lucky enough always to be with company that were embracing cloud and AWS. So basically, I have a lot of experience scaling, and kind of this presentation is a lot about all the mistakes and the failures I've had, and kind of how you can maybe avoid them. And I'm going to talk a little bit about cloud, but actually some of those patterns apply to anything. It's really kind of patterns around programming. Before we get started, I'd like you to kind of figure out and try to guess what's going to happen here. Any of you know that particular incident? So there's so many things that could happen here. I like to see these videos and kind of see this live situation as a microservice, as an architecture. Basically, you know, there's I think the guy is like this request, you know, that comes from the client, and maybe a rogue request. We don't really know what's going to happen. It's touching the backend. It looks suspicious, but we don't really know what can happen. There's so many things, really. So that's pretty much, in my opinion, what happens in microservices in an environment. Is like something happened, and then all of a sudden, this bad request takes the entire service down. Now, this actually by itself is quite funny and interesting, and there's a lot to learn out of it already. Should the entire barrier be locked together, that if you touch only one part, everything goes back? But I think the courage here is trying to bring this back up, and everyone realize that it's an impossible task. And this is really what microservices are and the real world. And I think if we can agree on the definition for today and out of this talk is actually failures happen all the time. And there's no way nowadays you cannot embrace failure and architect your environment and systems without embracing the idea that failures will happen. It's not if, it's really is when they're going to happen. In the last 12 years, I've seen crazy stuff happen, taking the entire data center down from a squirrel to a shark, to northern lights, to drunk drivers, actually a few times. Really anything can happen, and you can have the most beautiful code. If you haven't thought about this particular type of failures, basically your system will go down. So how do we build this kind of systems that can handle failures, right? That can embrace failure as a first-class citizen. No more, I'm scared of failures, let's try to design applications that never fail, but instead design applications that can handle failures and that will embrace it. And that's the whole field of resiliency engineering. And this is kind of what I'm really specializing in. And the idea of resiliency engineering is, okay, how do we run a system with failures? And there's a special mode for that. It's called partial failure mode. And this is actually, instead of me trying to explain you what it is, this is the best representation of what partial failure mode is. It's a taxi driver in India who has a flat tire, but instead of stopping his course and doing a fix, he actually implements a hot fix in production and continue delivering his customer to the destination. And this is really what resiliency is, right? Is how do we take an entire system that is partially failing, but continue the task that we're doing. And this talk is around giving you ideas of how do we do things like this. And one of the most important things when you design around failure is blast radius, right? Because at the end of the day, we want to minimize the blast radius. And for us, when we design system for our customers at AWS, or when you design as a customer, you always have to think about that particular blast radius. How many customers is it going to be that my failure is going to take? How do we, what kind of functionality? How can I take that functionality and kind of push it away from the main architectures? How many locations is going to be handled? How can I maybe architect around several locations? If one is failing, shift traffic to an entire region. Exactly what companies like Netflix are doing. And we need to talk about availability a little bit before we go into that. How many of you know this equation? few, right? A little bit. Actually, this is pretty much the most important equation you have to know when you talk about architecture. Not only in the cloud, actually, this is an equation that also comes from electronics. Is the equations of redundancy and availability in parallel. So if you have a component that, for example, is only 99% available, which is pretty bad because that's in a year 3 days and 15 hours of downtime, and really that's not what you want. But if you take that same component, you don't do anything else but just put it in parallel with another one, you boost that availability to 4 nines. And that's pretty amazing work right there, what you just did. If you do that 3 times, you reach kind of 6 nines of availability, and that's kind of world-class top of availability. You haven't done anything else with your component. It's still the same as itself. It only has 99% availability, but if you duplicate that, then it becomes highly available. And this is really the whole fundamental equation that governs many decisions that are done when, for example, AWS builds regions. You know, when we build regions, we take into consideration the geographic locations, and we have several regions, right? I'd like to deep dive a little bit on those regions to tell you how these equations affect that. If you deep dive on one region, say, for example, the Frankfurt region, since it's not too far, it's a multi-AZ one. We call that a region comprised of 3 AZs, right? An AZ is availability zone, and one AZ can have 1 to multiple data centers. It always starts with 1, but eventually grows to multiple data centers. And that's simple 1 AZ. Actually, some of the biggest AZs in US have 14 data centers. And if I tell you one data center holds about 300,000 servers, right? That gives you kind of the scale of operation. There's quite a few of those AZs in some certain regions. Some regions have up to 6 AZs, right? But all our regions have nowadays at least 3 AZs and plenty of data centers. And this is done simply because of the mathematical equation, right? We call that multiple AZs. And all those actually linked with high bandwidth network so that we can do synchronous replication. Actually, all those buildings are not just across the street. They are a few kilometers apart so that they have different power grid, different floodplain, different fire plane, all these kind of things so that if a problem happens in one AZ, all the other AZs are isolated. And this is exactly what we talk about, right? Redundancy in parallel. So if you do this kind of applications, you are able to design applications that are extremely highly available, even if your single application itself is not necessarily super highly available, but just by putting it across 3 AZs, you increase the availability of your application very fast. And this is kind of the central patterns for all the applications that you would want to deploy in the cloud. Make sure that you don't have it deployed in only one data center, that really across multiple AZs in one region. You don't necessarily want the data to move from one region to another, but have that at least nailed down. And this is really the basic AZ architectures that we also use for our own services when we design those. But I want to go show you a little bit. This is the redundancy. Of course, if one AZ goes down, the systems will shift traffic to the other AZ, especially the load balancer can detect that kind of things. We would have a standby that is automatically promoted as master, and then your application is still running. And these are really standards. Many customers, some of the top biggest customers in AWS are using something like this. And this is really simple to do. The only thing you have to do is simply have an application that is handling stateless, so that if an instance is going down, the state can be taken by another instance and then be repeated. Okay. And this is what is there. So very often we see customers keeping state inside the machine. I think it's a very good practice to have, let's say, another data store, Elastic Cache, Redis, or NoSQL database to be able to push the state of the application away. So that kind of standard cloud. But I want to talk a little bit more about some of the useful pattern, and Venkat talked a little bit about asynchronous pattern, and this is kind of a similar things, the idea of decoupling. Very often when I see customers having outages, it's because things are really coupled, highly coupled with one another. So you see, for example, that person that tried to go across the street to the entire system down. If you would have a highly coupled system between your API and your backend, it probably things like this would happen. It's called cascading failures, right? But a very good way to isolate things is to decouple them and put, for example, queues between your API and your worker instances. It doesn't mean the entire application has to be that. I'm working with some bank currently, and many of their APIs are synchronous. For example, when you want to send money, you don't want that to be asynchronous. But many of the other APIs for the applications are absolutely asynchronous, right? It's not, it doesn't have to block the entire set of services to be able to do that API. So I'll always go through the entire API, figuring out which one is synchronous, which was asynchronous. And if you have some asynchronous, then I think this pattern is beautiful. The pattern is simply you put an API, and instead of returning, instead of trying to do that API right away, you return a job ID, and then the client kind of get that job ID. It doesn't get the result of the task, but simply the task is then put into a queue and then eventually can get done by worker instances when they have the job done. You have to imagine that this is a very interesting scenario when you are in an outage situation, right? We're talking about resiliency. There's a failure in the system. What you want to do is preserve some of the resources of your system. So having the worker instance take the data from the queue when they can is very, very good, because if they are busy or doing critical things, you are not making them even more busy with other stuff, right? I always say it's the same things, like if you have kids, the kid is in the car and say, Dad, are we there yet? Are we there yet? Are we there yet? Instead of, hey, Dad, tell me when we arrive. You see the difference here. Dad can then focus on the road and not crash the entire car. And I think this is a beautiful way to think about it. Then when you get the job done, you can put it in a cache, and then the result can be fetched then by the client. The interesting things here is that you can also scale the API from the workers very, very differently. Actually, very often, API endpoints, when they are not necessarily heavy or heavily used, they are CPU bound. But as soon as there's a lot of concurrent correction, if you kind of use them at 70, 80% of the resources, you see the impact of memory is actually increasing a lot. So then you can have more kind of fine-tuning between the APIs versus worker instance, which might just be CPU bound or memory bound, or any other kind of metric that you want to use. So this is a beautiful pattern. I mean, it sounds really simple, yet it's very, very few people are necessarily using it in production. How many of you are currently using this kind of decoupling system? Yeah, just one or two hands. And yet this is really a pattern that can prevent a lot of problem. But this is not necessarily the best thing that it's decoupling. The most interesting thing here is that, of course, the client can fetch the result later by receiving a push notification. But the most important thing is here the queue system, because now when you have an outage, you can start deprioritizing requests. So in all your applications, you have critical APIs and non-critical APIs. And in an outage situation, what you want to do is not treat every request the same way. Who cares about the non-critical API? Who cares about the API, hey, I'm updating my profile pictures versus, hey, I need to send money. You see the difference here, right? Or I want to have the balance of my accounts. There's different ways in kind of a way to treat an API. And these kind of patterns allow you to create different queues or have a priority within your queue when you are in an outage situation or in a failure situation, so that you can actually degrade and treat only APIs which are critical, instead of saying, sorry, we are in an outage situation, we don't do anything. So this is very important. Look at your entire API spectrum, look at what is synchronous, asynchronous, and then try to eventually think, hey, which are critical and which are not. I want to show you a little demo, a little bit about that pattern at work. Unfortunately, all the code is going to be in Python because I do a lot of Python talk, and this is. But like Venkat said, I think being able to be multi-language is very good, and you can probably read it. This is an application which is running locally, and I'll tell you what I'm doing every time. Before I worked with AWS, every time we hired people in our engineering team, we will put the first week at a task to make them aware of resiliency and failures. And what we would do is, hey, design a system with 3 APIs. One which is an echo API, which is a ping API, a health check, which is more like a deep health, deep echo, so you look at all the dependencies, and then a product API, which you can put and get. And simply this, and then the task was put it as, make it as resilient as possible, use Docker Compose so that everyone can start playing with it and start breaking things at the end to see how well you've managed to implement resiliency. And this is a very interesting exercise. Actually, this is kind of one of the one I built, and it's on GitHub as well. But I want to show you a couple of things. So it's running an API front end. There's a decoupling between the API and the workers here. There's a task running, and then there's a load balancer using Nginx. And then there's a master database, a slave database, and then these are my cache and then the queue to be able to pass message between the API and the front end. And this is the whole system running. So you see, it's called Eleanor, and the API is up. And then Eleanor, you can do something like this. You can get the health check. You see, so my DB master is up, my slave is down, is up, and all that is work. And what you can do is you can put task into the system, and this is to exactly show the decoupling pattern. And then here my task is being returned to the client, and when my client has time, then I can do, get that task. And you see, this is the result of my task. And these are very interesting patterns, as I say. They are not difficult to implement. There's few things to think about, and we'll talk about that in the rest of the talk. Okay. So degradation is very important. Now, when you start to implement kind of decoupled system, asynchronous systems, or distributed systems, there's few things that always end up in an outage. And those 3 things are timeout, backoff, and retries. How many of you have had outages because of non-implemented timeouts? Few, yeah. Retry storms, these are deadly, right? Yeah, exactly. Yeah. So I'll give you an example, and this is kind of the most common example to prove the point what I'm trying to say. This is a user trying to put data into a database, and usually we use an app, and then we implement our system well, so we use a connection pool, right? Kind of the way to do it. Now, the problem is in an outage situations or in a kind of hard situation, our database kind of regularly start to slow down. And this can happen for many reasons. Maybe there's a hot partition in it, the sharding has been badly done. Nonetheless, it starts to slow down. We've had these outages a lot with customers. This just always happen eventually. So your customer is trying to put data into the database. My database starts to slow down. What happened? Anyone wants to give a guess? What could happen here? What could possibly go wrong in that scenario? Yeah, so let's think about that, actually. Let's talk about how this, there's few things we need to figure out before the connection the connection pool is running out, is actually what are the timeouts, right? Because if your timeouts are well put, usually you don't have connection pool draining. But in that case, let's say we are normal developers and we trust our dependencies, we trust the libraries we import, and we use default timeouts or system timeouts. What are the usual default timeouts on backends? How many C# developers here? So the HTTP client library for C#, what is it, the default timeout, do you know? Huh? It's like not so sure. Python developers here, a little bit. Python requests, default timeout, infinite. C#, 100 seconds. So it's a lot of stuff. Actually, when we did reviews of all the default timeouts, very often the minimal is 100 seconds. The rest is everything which is between 30 minutes, 60 minutes, infinite, right? And these are documentation. I'm just not making this up. You can actually see ASP.NET as well, 20-minute timeout. There's a lot going on in 20 minutes, right? My request or the customers which is trying to play his videos or things like this. Get socket timeout is a cell, usually a negative value by default -1. And this goes system default. So basically, you have no idea what you inherit from your system. Timeout for Python is infinite, and this goes on, right? This is the web request for library for .NET Core, and this is 100 seconds. This is the MySQL driver for JDBC driver, default 0, infinite timeout. So let's take that, we use the defaults. What happened then? My user is actually making a request, and there's an insert, my database slows down. Well, my default timeout on the back end is usually over 100 seconds, and the default timeout on the clients usually is 15, 20 seconds. So let's take a 10 seconds. Actually, client timeouts are a lot better than the rest, because I think client libraries are more aware of customers' pain, so that they want to have faster timeouts. I don't know why on the back end it's traditionally very, very bad timeouts defaults, but that's the way it is. So I have a big problem here, you see, because my database slows down, my request can't be processed in 10 seconds, so what happens? Well, my timeout client starts to kicking, but my connection pool stays connected because there was no timeout there. I'm still at 100 seconds. My client is kind of, smart, trying to do a retry, and exactly what happens, I suck up all the connection pool eventually in the system, and that goes very fast, right? So we've had outages with prior to joining AWS, I was running a company, and we had outages literally in 16 minutes. 160 servers went down because of that. And it was a dependency on the Redis library, which we imported the library, we forgot to look at the default timeout, and that's what happened. So that errors happen. You've had that error a few times, failed to get connection for, right? This is exactly the scenarios. It's an exhaustion kind of failure, right? So we run out of things. That means your app cannot get any more APIs because nothing happens. So the question to you first is set the timeouts. How many of you introspect all the libraries that you use and download from NPM or Java class, all the things? Do you actually look at the timeout to have a spreadsheet of all the default timeouts in your backend? How many of you do that? You are amazing. There's 1.5 person doing that. So this is super important, right? Because it will go down, it will take your system down, and it's very, very hard to figure out what's the issue with timeouts. Right? Why is it difficult? Because very, very often they are encapsulated in other exceptions, right? So you have to de-roll the entire exceptions and then go to the source of truth. But where do you set the timeouts? Well, that's another good question. So if you have 4 or 5 dependencies, where do you do it? Well, a very good way is to set it on the client and actually to pass it as a parameter for your request. Right? So the entire dependency in your backend kind of can figure out what's the budget I have for a timeout, and then can set it along the way. And this is kind of a nice way to set it. Another one is, when your client timeout is actually make sure that all the connections that have spooled from that initial connections are actually timed out as well. That's much harder to do. Very few framework can support that, but it's something that also can be done. If you add an ID to each of the requests, and then you can make sure that each request gets canceled or timed out when the parent request has been happened, this is things that you can do, but it's very hard. The easiest way is really to pass the first timeout as a request parameter so that the other dependency can inherit it. Now, what else could you have been done with that? There's actually quite simple things that could have been done to prevent that error. Yeah?
You mean was the problem we can have in the script? So we can have inconsistent data. So for example, first and third is that if you don't specify the ID and they give us
correct independency. Yeah. Right. I'll talk about that a little bit later. But actually, how you could have prevent that big failure as well, like running out of connection pool. What's that? Yeah. So one of the very easy way to do it is do what we call a back off, right? You make the first request, you retry after 2 seconds. If you don't get it, you retry after 4, 6, 8. Now, this is a very easy way to start freeing connections from the backend, right? Because if you have a timeout backend side 10, then you're good with your timeout. You see, you release connections. Now, the problem with backoff, if you just do an exponential backoff, is that the retries in the distributed systems are still kind of clouded together. And this is a research paper we published in one of our blog about different mechanisms and different exponential backoff. And you see the call counts on the left without jitter is still kind of distributed within the same area. So in the distributed system, even though you do backoff, all the system will retry at the same time. And retrying at the same time has very, very bad effect. It's called retry storms. That means you exhaust actually network resources, bandwidth, and the system also get very tired. So a very easy way to avoid this kind of the distribution is to add the small jitter. A jitter is simply a random, kind of random number here that you inject in your backoff, right? And that makes actually life easier. I want to show you a little bit what this kind of backoff can do. But first, I want to show you what a retry. So this is a task. I'll show you the code first. This is my task. Task retry, and you see here I've done something smart. I had max retry, but this is a simple retry, and very often that's how people would do it. They would make a task and they would encapsulate with a default retry delay 1 second, and I've seen that all over the place. Now let me show you what this can do. You see, so this is a task that I returned the ID, but it never succeeds. Right? There's a failure in the task because it's trying to divide by 0. So of course the task is not failed, but it retried every second. And you can imagine in the distributed system, if hundreds of machines start to do retries at the same time, actually the biggest problem here is not necessarily the retry for the network, is the logging. I've seen so many systems and large architectures failing because there's no more space in disk for the logs, right? And this is one of the big risks of retry storms, is actually the log that is generated from all the retries. Right? So there's two things here to do. If you realize that you are in a retry storm, one thing is monitor your disk. If you have little space, stop logging. And this is super important, because otherwise you will start logging in a retry storm and your disk will be totally out of space. How many of you had failures because of your instance or your disk running out of space? Yeah. And
sorry, if you have a question, we can give you the microphone and you can answer.
Oh, I thought it was Alexa. I was like, I don't have Alexa with me.
Sorry.
It's like, thank you. Alexa, if you have a question, please keep the microphone. Awesome.
You can raise your hand and I will come to you.
Yes, yeah, don't hesitate. So this is something very important, right? So when you do retries, don't do a stupid retry. You can do a retry which is with a backoff, and you see, no, sorry, it's called the expo, of course. So here, my task is still failing, but I have a retry after 4 seconds here, after 62. And it's much more gentle with the system. You see, I only have 2 lines of logs, and I already have 62 seconds to wait for the system to digest that and try to recover. All right, so something to very easily keep in mind. And this is so easy to break system with that. All right, so first, when you have retries, make sure you don't retry every second or even in a loop. 1 second is gentle. I've seen system retry hundreds of times per second because then it was in a routine, and then it's prone even more threads, and this whole system kind of went bad. Another important thing here, and I'll make my point with the next slides, is of course what the gentleman said, is your requests need to be idempotent. Right? So if you have a request to put data in a database and you have many retries, well, maybe that request will happen several times. So let me show you in code what this means. So this is the product API, right? And my code is currently handling, I can put a product into the database and then return success and then the ID of that product, right? If I don't add idempotency, this is kind of what happened, right? So let me save that. And then I'll store data into a database, and this is a product that already exists, right? I have Samsung TV Multicolor 2. Here I'm trying to store a product called Samsung Multi TV 2, and you see this is a request that will create an internal error and then logs, right? And this is terrible because in a retry storm, again, you might get that. The good thing is I still don't store the data into the database, right? Very often I would see a source system that would treat that request and store it again simply because the index is badly done. But in dependency, we'll treat this like this. So you kind of look more or less if your product kind of exists before putting it, and then you can return the exact same thing that if you would have posted before. So let's try to post another one. I'll show you that the request is exactly the same. So here it fails, and then if I have my product exist, of course this is live failure. I have not implemented idempotency well enough. So this is just proving my points, right? We're doing tests, and actually I find out that there's another error in the code, and this is something to figure out. Okay, good. I need to fix that now. Cool. So, idempotency, very important. Another thing, what would have been very important here to prevent that error to happen in the connection pool? Well, let's look at this, actually. This is a diagram that is very classic in distributed systems, right? This is a system going well. We have services using a recommendation engine. Actually, this is how Prime Video, Netflix, and kind of work. They have different services, and then they can call one service to do recommendation engine or to do recommendation for people. If my recommendation engine starts to slow down, I have similar things happening, right? So I have retries from the clients happening, eventually retries from the backend, and what happens is, of course, these become very hot zones. So first thing first is actually preserve this at all costs. And when you design system, you have to think about that. And you wouldn't think about this if you don't think about failure, right? So when you think about failure and you say, okay, when my system go down, where are going to be the hot zones? So here there's clearly 4 hot zones because what you want is prevent more requests to come in the systems. And there's clearly a few things that could have saved the system. We talked about timeout, that was one. We talked about retries, but actually max retries, right? And I showed it in the code. Very often you would have retries, in loop retries. I've been in 2 outages where actually in distributed systems, there was about 10,000 clients, and few of those clients, literally a handful of them, went into a retry loop, infinite retry loop, and took down the systems, right? And that's crazy. Right? So max retry is one that could implement. If the max retry fails, what could you do? Well, rate limit. Super, super important, right? So That's something that has to be done. So let's look a little bit at an API here that is called Echo, right? This is my Echo API. I can call that like this. My Echo API basically just tell me it's up and running, it's good. So these are what we call shallow pings, right? Very often application would have that to figure out if the system is good. Now, let me show you what a retry storm does. So let's open a new horizontal plane and let's launch that. So this is this, and I'll remove I need to remove rate limits here because it's implemented, and I want to show you what happened. So here what this does, this request, it actually is going to launch 12 threads with 400 concurrent and then request, and then DDoS for 20 seconds. Right? So here is what happens. It's not logging because I removed logging, otherwise you can imagine what would happen. But now if I do that same request, you see how long it takes for the system to answer. And this is simply locally, right? Versus almost immediately. This is how your system impact. Now in a distributed system, now it's done, you see the answer much faster. In a distributed system, the impact of having this kind of closed loop calling an API are really, really dramatic. Right? So very simple way, of course, is you introduce rate limits, and then once you have a rate limit and you call that few times, there you have a slowdown. And this is kind of almost a silly way to implement rate limited because it's still in the backend, right? But we still return immediately. We have a rate that is excluded, so we don't process the data, we don't do any stupid stuff. So any APIs that would have been pretty dangerous, like require computation, would have been slowed down. Another good way to implement that is, of course, on Nginx. Okay, if you look at the configuration on the load balancer, is very easy as well to think about this kind of rate limits. Okay, and most of the services, if you use AWS, like API Gateway or the load balancers, kind of support this kind of rate limits. So think about implementing those timeouts, the max retries, and also rate limits, because these will literally save you a lot of outages. Okay. And the last thing is rejection, right? And this is kind of close to rate limit, is that you say, okay, now my backend is at max utilization, I'll shed the load, I'll just won't accept any more requests, push that somewhere else. This is really the extreme one. But bear in mind, we are trying to preserve a system that is already in failure mode. The last one is an interesting idea. It's a lot of people believe it's the answer to everything. I don't. In very large distributed systems, circuit breakers can be hard, but in most systems they are very interesting. Circuit breaker are. How many of you use circuit breaker currently? There's few. Cool. Circuit breaker kind of protect your function call by wrapping that into an object, right? So instead of calling a dependency directly, you wrap that into an object, and that object kind of monitors the dependency, how many errors, and then you can have a set of thresholds. All that is defined kind of in a configuration. So that's why it can be hard in the distributed systems with many circuit breaker to have the right configuration. But it's very interesting. For me, the most interesting thing with circuit breaker is when the developer starts to use it, he has to think about failures, right? Because you define your object, but you have also to define the fallback. What if my object or my circuit break? Then I have to think about the fallback. And just having the developer having this mindset actually can change the entire culture of a company. I've seen that firsthand, right? And then has wonderful effect to the rest of the things. Now, one thing I like to talk about is kind of resiliency, and how do we test this kind of system at scale? And how many of you have heard about chaos engineering? It's few, right? So chaos engineering is kind of in the field of resiliency, is how do we test those distributed systems? How do we provoke a failure in an experiment before it happens in production and before we have to really pay the high price for it? When Amazon started to scale in the mid-2000s, we brought a guy called Jesse Robbins. You see, the Jesse Robbins title was Master of Disaster in the Availability Program. I think that's the coolest job title you can have. But Jesse Robbins was a firefighter. A firefighter fight in a controlled environment, or trained fighting fire 80% of the time, approximately. They do that so that they can build an intuition so that when they go and fight real fire, they don't have to think. It's automatic behavior. And basically, Jesse Robbins wanted to bring that idea within Amazon so that in case we were having outages, and we were having outages a lot because at the scale is insane, we had to train people to handle failure and test the system for failures, right? So we brought a system called Game Day, and Game Day is very similar to what is called now chaos engineering. Basically, Jesse Robbins would go around the data center and unplug things randomly and then test what happened when I unplugged the database. What happened if I unplugged the ERB? Actually, he went into putting down an entire data center electricity down to test it in production. He did it once. There was big consequences to this one. But it started the whole revolution into how we test system at scale. And nowadays, we still do game days at Amazon. There are a lot more contained experiments, right? And this has been made very popular by chaos engineering, which is a term coined by Netflix. And they've done that through what they call the Seaman Army. So Netflix uses 4 regions on AWS across the world, and they needed a new system to be able to test what happens if a region goes down. So they've done a lot of what they call monkeys to test the system in production. The small monkey is the first one there in the middle, is randomly going in production, killing instances, and the big gorilla is actually going in production once a month roughly, and it kills the entire region in production. So Netflix can then test at scale what's the impact of region failure and then shift traffic from one region to another, and they do that in 10 to 15 minutes roughly. So it's brilliant. Something that has to be said, it's not doing things randomly, chaos engineering. You just don't go walk and break stuff. So don't go and see your manager on Monday and say, hey, Adrian did a talk on chaos engineering. You say we should break databases, and then you go, you remove it. It's not gonna work, right? You have to think about it as science and approach it as a science. It's a control experiment. There's tons of things to do. You start from an hypothesis. When something goes down, what will happen? Take everyone around the room, discuss that thing, because no one will have the same ideas. For example, if you take an entire engineering team plus the managers plus the UI designer and say, what happened to my application if I take the database down? Well, everyone's going to have a different story, right? So you have to go through the entire process so that you can build confidence in your system to be able to withstand turbulent conditions, right? And this is something I wrote in my blog. And there's few ways to do it. One simple way is vaccination. It's called failure injection. You go around and start to inject failures. You saw me using the WRK command line. That's a very, very nice way to start injecting failure. It's like, okay, how are you going to DDoS yourself? How is your system going to be resilient? And you see, you can have a lot of level. There's a people attack. This is one I do a lot with customer. It's not that I break the neck of people. We all have this guy in our companies that does everything. He's super genius. He can fix everything. Usually I try to identify that person, and then I take his laptop and I say, you go home. And I've done that 3 weeks ago with a company. They lasted 6 hours, right? Before we had to urgently bring back Paul into production to fix everything. And that, the company started to realize the big problem, right? It's the bus factor, right? That's a failure. It's a human failure as well as technological failure. So I want to show you a few tools. I have 6 minutes. So this is one of my favorite as well. And I've used this. How is your system going to behave once you kind of try to DDoS yourself? You see my Echo API behaved quite nice. It was a bit long, but it still answered. Many of the system, as soon as you DDoS them, start not answering. Simply this is a very good way to do resource exhaustion, right? This is on the API called health, which is calling all the dependencies, so you can imagine the impact on the application. So I'll just show you that because it's funny to see. So if I take my health API here and I remove the rate limit, right? I remove the rate limit and then I do the W on that API. Now, the good thing is actually I also implemented cache on that API, so it's not as bad. But you see, first the logging is going nuts, and then my health API is actually very, very, very slow. You know what happened in the system when you do that? Well, the load balancer will think, oh, my instance is not responding. I'm taking it out of the pool. That's what happened. Right? And that's exactly what happened. So this is a super, super easy way to test the system. So I highly suggest you try to do this at home and in your environment. Just bring your application inside Docker. It's a beautiful way to find small problems. Another way I love to do that is using the TC command. This is to add network delay between interfaces. So here is adding a 200 millisecond delay in your ETH0 interface. This is a very nice way to start creating latency between systems. Latency is devastating, right? It's actually one of the hardest things to fight against. So this is a very good way. Of course, the Siemens Army I talked about from Netflix. Now, I love the Siemens Army, and actually, they're pretty cool. They are more like scheduled agents, so it's like a cron job type of things that you schedule, and it will start randomly do things. Now, the only problem I have with Siemens Army is that it's integrated with Spinnaker, which is the CI/CD platform from Netflix. So if you don't use Spinnaker, it's actually pretty difficult to use the Siemens Army. But the code is still there. There's tons of stuff that you can kind of learn from, which I think is great. One of my favorite is the Chaos Toolkit, and that's kind of an open source project. And it's an open API where you define kind of a scenarios. So I'll show you how it looks like. So, yeah. So this is an experiment defined with Chaos Toolkit. It's a JSON file, and basically it kind of tells me here what is the impact of terminating the master database in my application. And then I go into the experiment. So first I need to figure out the steady state. What is it before I start breaking stuff? How the API is supposed to answer. You see it's supposed to answer within 15 seconds with a tolerant 200 check. And then the method, I'm going and stop the Docker container here that has the master, and then do my experiment. So you get the idea. This is a very nice way to create easy experiment and put them in a CI/CD pipeline. And I like that it's an open source project. You can modify the extension, add your own extensions. There's a lot of cool stuff being deployed. So if you can, have a look at it. Another one, and this is in the presentation, so you can have all that. Another one that I really like is called Gremlin. Gremlin is a chaos as a service. So I'll show you in practice what it is. This is Chaos, the Gremlin interface. You simply download an agent. You can put that in a Docker container or in your instance. And that agent talks with the interface. And then you can start doing attacks. So here, let's say we can create a new attack on my system. It goes inside my environment and finds that I have an instance here. And then I can start choose what kind of attack I want. I can do a resource attack. I can attack the CPU, and let's do that actually. So let's connect to my instance. Okay, I need to add that. Cool. and then let's run a top. So this is my instance here, and it runs pretty nicely. You know, there's no attack yet, but let's do a resource CPU exhaustion. So it will last 60 seconds, and then I can unleash it. And you'll see very fast my attack is there, is going on. And the Gremlin daemons are now running, and you see it does a resource exhaustion on my machine. So that's a very good way to see, oh, how is my application now going to behave once I'm killing the CPU of that machine. So it's very similar to adding latency, is how my application is going to behave. Now the good thing with this one is you can alt attacks immediately if you see there are problems, and that's a very nice way to do it. And it takes a couple of seconds, you see here, and then my CPU hopefully will go down and Gremlin is dead. There's a lot of different attacks you can do. This was just a CPU attack, but you can do pretty cool stuff. So let's show you a few of those. You can do a state attack. You can start killing processes randomly. One I love is called time travel, is to change the time on an instance. In a distributed system, this does beautiful things. Usually it breaks them. So if you can do it, experiment with them. And this is, as I say, what I love with chaos engineering, because I'm running out of time now, is that it tests the unknown, right? When you write tests in your application, you usually write tests against things you know, right? Versus chaos engineering and resiliency engineering, it will make surface things that you have never ever thought about, right? And sometimes things that are super simple, like a timeout, adding simply a max retry, or make sure that you prioritize API. I wanted to demo this one, but I'm running out of time. So have a look at Toxic Proxy. Toxic Proxy is beautiful as well. It's a proxy you put between your clients and the things you want to test, and you can write toxics. It's basically one line of code. You can add things like this, because I can show you quickly. You would do something like this, toxic, and then you can add a toxic, and this is so this is adding a toxic in the system, which adds, in that case, 1 second of latency between my proxy, my client, and Redis, and then you can start experimenting, see how is the system going to behave. I love Toxic Proxy. If you are into Kubernetes, there's implementation of the Chaos Monkeys for Kubernetes. And then Pumbaa is also something pretty cool to do for Docker instead of doing it yourself. Tundra also has some cool stuff happening to do test Lambda functions. And I also wrote a bunch of things for serverless and Lambdas, how to test inject chaos in your Lambda functions using layers. All this is available on GitHub to download. All the code that I showed today as well, even though it's Python and you might not find Python sexy, is just at least all available on GitHub, so you can start experimenting and see how things fail. And you see, even in demos like this, I try new stuff. I find the system is failing. So what I'm going to do today is try to make it more resilient. To learn more, have a blog there. You can go and see tons of those articles that have deep dive into the topics I talked today. And you can also hit me on Twitter. So thank you very much for your time, and have a great end of the conference. And if you have any questions, just I'll also
raise
be
your
on the
hand,
side.
and I will give you.
We have time for questions now?
No.
Okay.